The evil is over, guys. You can rest now. Trigonometry. It's finished, baby! Yeah, yeah, yeah! Trig is finished. Oh, yeah, I know you guys hated trig. I was having a rough time with trig myself, and honestly, well, we were about a month and some change into doing trig. I'm ready to switch gears, guys. I know that was a hard unit. Now you're looking at this, you're like, calculus, huh? We knew this day would come. We're going to learn calculus. I'm going to be bad at it. I'm not going to do well. I already had trouble with trig. How am I going to learn calculus? Just everything you know about calculus, or what you think you know about calculus, just put it to the side, okay? I'm going to walk you through this. Trig is hard, okay? Trig is hard, no denying it, and calculus is hard, but it's a different kind of math. It's a different way of thinking, okay? So if you didn't like trig, doesn't mean you won't like calculus. So give it a chance. Let's first talk about what calculus even is, okay? Well, so calculus actually has a really interesting history. It hasn't been around that long, actually. Basically, what calculus is, we're going to kind of build to it, but calculus has been referred to as the granddaddy of math. It used to just literally be called, math used to literally be called calcula, which is basically calculus. Like, calculus literally meant math, okay? So imagine a subject you're learning, and that one little bit of that subject is the name of everything else, right? It's considered maths. It reminds you of calculator, like calculating. It literally is that. It also actually means, the Latin name for it is little pebble or small pebble. And this is kind of like a dental term that they might use. If you go to the dentist, they might say, ooh, you got some calculus on your teeth, which is not good. That means you got like bad stuff in your teeth, right? And maybe you gotta get a filling, all right? So they might say that. But calculus, it was called small pebble because it literally meant, before we got calculators, they used the abacus. And so that was kind of one way to like count and measure stuff, was with small pebbles, right? So calculus has a lot of different meanings, and let's kind of go through this. So algebra was all about relationships. Geometry was all about shapes and space. Probability is the math of chance. Calculus is the math of change. The math of change. Which is kind of a broad term, right? There's so many different things that change all the time. So how do you even measure that? What do you even do about that? Well, we're going to talk about that today, okay? Calculus is very interesting. It was developed simultaneously by these two gentlemen right here. Gottfried Leibniz, I probably butchered his name, I apologize, and Isaac Newton, who needs no introduction. We're going to talk more about Isaac Newton, but this Gottfried guy, I mean, they developed it at the same time, so he deserves just as much credit for this as Isaac Newton. It's not all just the Isaac Newton show, okay? Having said that, we're going to talk about Isaac Newton, okay? So, a story of gravity. You may have heard about it before, okay? Isaac Newton was sitting underneath an apple tree. An apple fell to the ground. He observed gravity, and he came up with all these formulas, and yada, 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 okay? Well, when you watch this apple fall from the tree, the story goes, he looked up at the moon as well, and he noticed the moon, that guy's not falling down. Why are these falling down, okay? It turns out, and this was after many developments of physics, it turns out that as an object gets close to another object, the force of gravity between them actually increases. Whereas an object moves away, force decreases. So the force of gravity is always happening. I mean, there's stars and distant galaxies that have their force of gravity acting on us, but it's just so far away that we don't feel the effects. The moon, however, is close enough to where we do see the effects. We see tides, right? It's just close enough to where that happens. Well, this is kind of what's going on. The force of gravity is inversely proportional to the r squared. R is referring to the distance between objects. So graphically, you get something like this, where as you get really, really close, your force of gravity is way really high. But when you start moving your objects further away, the force of gravity goes really small. And obviously, that is not a constant change of force, right? And you can see it graphically. Yeah, there's a really, really steep change, right? And then it kind of gets a little less steep, and then it gets really, really flat. It's not constant at all. So he was very curious about measuring that change. He wanted to kind of know about that, right? He wanted to see how the force of gravity is changing by distance. And so how do we actually measure steepness? How do we do that? This is our good old buddy pal, the gradient, okay? We're going to return to the gradient, talk about the gradient, because he's going to be really, really crucial to our understanding here, okay? The gradient is equal to m, which I have no idea why, and that's equal to a rise over run, right? So if you have this line right here, we have these 2 points, and I want to compare them. Well, the rise is obviously the vertical component, the run is that x component, the horizontal, and the ratio of them gives you your steepness of your graph, right? The alternative form of this is m is equal to, if we're talking about points, x1, y1, and x2, y2, this is the change in your y components, y2 minus y1, over x2 minus x1. So rise over run as well, okay? Now, if we look at this guy over here, and I try to do the same thing, well, I can't really do that. I mean, because like it's different over here, and it's different over here, and it'd be different here, right? There's different points along this line. We're gonna get different changes, which I guess is good, but we're getting infinite amount. The only reason this works so well is because we have a constant rate of change, right? Just because I got these 2 points and found that slope, well, that's the slope of the entire line. So it's awesome. So Isaac Newton looked at this and he said, well, what the heck, man? Like, I don't know what to do from here, okay? Let's think about circles for a second. You're like, I think we're jumping. What are we even talking about? Okay? Let's talk about circles for a second because they do come in handy. What if we wanted to get the slope at a single point? What if I wanted to do that? Okay? Because obviously if I do it between these two, that's not going to be the same as if it was these two or these twos. Or he wanted to know, where can we find the rate of change at a single point? Where can we do that? So we need to talk about circles for a second. Because circles have some interesting things about them. First of all, this guy right here is a tangent line. It's a tangent line. It's a line that touches. It goes through 1 point on the circle right here. Okay? And that's interesting because, well, if we look back, that's kind of what we're trying to get. We're trying to get a tangent line of this guy in a sense, right? Now, again, getting it at a single point, that's not super handy and helpful because, well, of our slope. Our slope doesn't really do that at a single point. We'll get 0 over 0, right? We need to talk about secant lines for a second. Well, secant lines are lines that cross at 2 points. So that could be here and here, right? So there's a secant line, there's a secant line, a bunch of secant lines, right? Now I want you to notice something. As these secant lines get closer and closer to the edge of this circle, look at their points. And I'll draw one more in between these two. Look at their points. They are converging. They're getting really, really, really close to this guy right here, okay? So maybe we can't calculate the slope at a single point, not with our means, but maybe we can get 2 points really, really, really close together and then get the slope of that, and that'll give us maybe an approximation. That's kind of what we have to work with, right? So we can approximate the gradient of 1 point by bringing 2 points really close together. Okay, so that's handy. Well, this is what we're going to do. We're going to look at 2 functions. 2 functions we've seen. Two functions we've seen before. We've seen x squared and we've seen x cubed, and I want to apply this idea of getting the slope at a single point, okay? So what we're going to do is we're going to draw, you're going to draw, because I already drew, you're going to draw the x squared function. So f of x equals x squared, and we're just going to do quadrant 1 for right now, okay? And I'm going to call a new variable, I'm going to call it h. And I'm just going to say it's a super small change in x, super small. Basically, h is approaching 0, I'm going to say. It isn't 0, but it's like 0.00000001. You kind of get the idea. We can make it as small as we want, and we're going to just pretend it's a super small change in distance. So if I am trying to find the gradient at a single point, I'm going to do it at this point, and I'm going to assume this point is really, really, really close. It's like we're zoomed in right now, okay? And I have a small change in my x direction, this little change in h, this little distance. So now let's write out what the x and y are going to be for each of these points, okay? So this first point, the one we're looking at, you might just say it's xy, but instead of using y, we're going to think about what it would be in terms of x for right now. Well, if I plug x into this function, I get back x squared. So that's my y value. That's my xy point I'm going to start with. Okay, now what are these points going to be? Well, now this is taking for my new x, this is x plus h. That's my x value for this guy up here. And so my y value would be, if I put this as my input, it would be x plus h squared, the whole thing. Why am I doing it like that? Well, I want to use my slope. I want to use the gradient function to kind of help us, or the gradient equation to help us, okay? I'm going to replace these y2, y1s with these guys up here, okay? We're just working with x's and h's right now. So my y2 is going to be this x plus h squared minus my y1, which is just x squared, okay? Now let's look at the x values. My x2 is going to be this x plus h. I guess I'll write that in red again. Minus my x1, which was just x. Let's clean this up a little bit. Let's see what we can get out of this. So x plus h squared is x squared plus 2xh plus h squared, and then minus x squared. Down here, it's just going to stay the same. Well, is there anything we can cancel out? Yes, we have some x squareds that can go away, and we have some x's that can go away. All right? So we are left with 2xh plus h squared all over h. Well, if I look up top, I can factor out an h and then divide it by h and get that to cancel out. Let's do that. All right. And so the h's, they're going to cancel out. So we are left with 2x plus h. And remember what we said about h. H is super duper tiny, almost 0. So I can actually kind of get rid of that guy right now. And I'm just left with 2x. And this 2x, apparently, it's the gradient at this point x comma y. It's kind of weird, right? That is a weird looking answer to get out of this. Okay. What just happened? All right. Well, this guy right here is the slope. Imagine a line, right? 2x. 2x is the tangent line at that point, is what we just found. And that is a linear function right there. F of x equal 2x. So even though that's a weird answer, it kind of, in a weird way, makes sense as well. All right. What we're going to do is we're going to make a table. We're going to make a table of some functions that we know about, and then we're going to write in the gradients. Well, the first gradient we got was 2x. All right. We're going to do the same thing with x cubed together, and then for your homework, I'm going to have you guys do x to the 4th, 5th, 6th, and then finally attempt to formalize it. Okay? I want you to try to discover some math and use these tools I'm giving you to kind of help you. So we're going to try x cubed now. Same exact method. All right, same exact method, so you can apply it to the 4th, 5th, and 6th powers. All right, and then we're just going to see if we notice any kind of pattern. Okay, calculus shouldn't be reduced to just patterns and stuff, but if you can use the patterns and use our formulas that we're going to develop, you can then learn to understand it better. Okay, right now, don't worry about trying to get it all at once. Let's just do this. Let's try it with x cubed. Okay. The derivative of the cubic function. We'll talk more about what a derivative is, but it is the derivative, okay, that we are finding. We found the derivative, or the gradient, right here. They're not interchangeable, but they have slight differences. We'll talk about it, okay? The derivative of the cubic function, we have f of x equals x cubed. So I want to find the gradient at this point right here, the slope of that point, okay? So once again, I have this little change in x, which is my h, super tiny, and I'm going to label these points. So this first point is going to be my x. That's what I'm plugging in. My y value here is going to be, well, if I plug x into this, I get x cubed back. That's my y value there. For my second point up here, well, if I plug in now x plus h, that is my input once again. But my output is going to be x plus h cubed. Okay, and those are my 2 points to work with, and I'm going to try to find the slope of that guy, or the gradient, either one. All right, so my y2, it's x plus h cubed. Let's go ahead and let's write that in there. Minus y1, which is now x cubed, all over x2, which is x plus h, minus my x. All right, once again, just like we did with the squared functions, I'm going to expand this out. Now, what would be quicker is if we used those binomial expansion rules. Remember, this guy is to the third power. That's our n. N is 3, so we're going to use that pattern. That's 1, 2, 2, and 1. Okay, so 1, 2, 2, and 1. Those are the coefficients. And then our first term starts at the third power, and then it decreases. And then the other one starts at the 0 power, and then it increases. Let's add those up. Okay, and then that's minus x cubed. Okay, 1x cubed. And then down here, it's the same exact thing. Okay, you might want to do that. You might want to use your Pascal's triangle or your binomial expansion notes to help you with these other ones, because it gets, it gets bigger and bigger, right? So we have, once again, same thing. X cubes, they're going to cancel out. The x's, they're going to cancel out. So what are we left with? We're left with 2x squared h plus 2xh squared plus h cubed all over h. Once again, I can factor out an h. So I have 2x squared plus 2xh plus h squared. And now my h's can cancel. I'm left with 2x squared plus 2xh plus h squared. And once again, I told you, h is super duper small. It's almost 0. So I can get rid of this guy. This has an h in it. I can get rid of that. And so I'm left with 2x squared as the gradient at this point right here that I was looking for. So let's write that in our table. It's 2x squared. I know what I did wrong. I need to review Pascal's triangle myself. These are supposed to be 3's, my guys and gals. These are supposed to be 3's. My bad. Good thing I caught it. That's supposed to be a 3 as well. My bad. 3x squared. Okay, we're good now. I found, because I already wrote this guy in. So 3x squared, it turns out, is the gradient at this point xy, just any xy point, when we are looking at x cubed. Now what I want you to do for exercise 6a, it's on page 129, you'll see this table. I want you to do number 2 and number 3. And really, they're kind of leading you to the same thing, which is completing this table. What I want you guys to do is formalize this, and then when we come back in class, let's see what you guys come up with, okay? It'll be kind of fun, I think. This is Mr. Knight, signing off. Don't worry about if you don't know everything that just happened. We're going to start building it together. It's new math, okay? It's brand new math, right? Have a good one.